My name is Jonas. I work at Blockstream as an engineer, and I'm going to talk about some primitives related to blind signatures and scriptless scripts. And in particular, I'm also going to explain a construction called a blind coin swap. And I'm also going to explain how to trustlessly exchange eCash tokens using Bitcoin. So since I want to introduce the so-called blind Schnorr signature, let's review Schnorr signatures. And my goal is not really to explain, or my assumption is not that you will understand Schnorr signatures completely after that, but maybe you will see that if you can understand Schnorr signatures, then the step to a blind Schnorr signature is not actually that big anymore. So for a Schnorr signature scheme, we first assume some group generated by a generator G, where the discrete logarithm is hard. In Bitcoin, we use points on the curve SecP 256K1. And a signature scheme consists of three algorithms. One is the key generation, which creates a new private key at random and computes a public key by multiplying the private key X times the generator of the group G, and then it returns this key pair consisting of the private key and the public key. Then there's a signing algorithm which generates a new private nonce at random, that's called K here, a public nonce, capital R, which is just K multiplied by G, and then it computes S, which is K plus some challenge times X, and the challenge is the hash of the public nonce, the public key, and the message. And the signature then is the public nonce R and S. Okay? And verification is relatively simple. You just check if S times G is the same as R plus the hash challenge times the public key P. Okay, and the point, of course, is that if you don't know the discrete logarithm of the public key, in this case X, then you're not able to create a signature which would, such that this verification algorithm would return true. Okay? So let's go to blind signatures. And the point with blind signatures is that the signer does not know the message it is signing, because this message is actually blinded. And also, after signing this message and producing a blind signature, this blind signature is unblinded such that it is unlinkable from the actual signature. So both blind signature and signature are not related. So usually this whole system is explained as a two-party protocol between a client and a server. There's a client knowing a message, the server doesn't know this message. The client creates a blind challenge from that message. The server signs the blind challenge, gives it back to the client, and then the client unblinds this signature. So let's see how that actually looks like. This is only 2 slides, so please bear with me. So the first difference is that the creation of the nonce and the signing are now 2 different algorithms. So first here we just create the public nonce R. Then the server gives this nonce to the client, and the client creates a challenge from that. And it does so by first getting 2 random values, alpha and beta, and then computing a new nonce from the old one. The old one was R, the new one is R prime, by adding alpha times G and beta times P. Then it creates the challenge, which is just the hash of the new nonce this time, the public key P and the message, and then it blinds that challenge, which I call C here. So just some random number is added to this challenge to blind it. Okay? So signing from the point of view of the servers, almost exactly the same as before, except that the server now doesn't have control over what it is signing. Previously, there was this hash where it would the message would get hashed, and now it just gets this challenge C, and it just signs it by computing S. Then the client unblinds this S by just adding alpha. And verification now is exactly the same as before. And this is very important because this means that in every system where you have Schnorr verification, you can use some sort of blind Schnorr signatures. Things that are usually built with blind signatures are, for example, eCache. And in eCache, you have a trusted server that maintains a database to prevent double spending. The server database consists of serial numbers that have already been spent, and the token is just a tuple of a serial number and a signature over that serial number. Okay, and then we need to define a single protocol that's called the reissuance protocol. It's also often called refresh protocol, where someone who has a token can exchange it with a server for a fresh, unlinkable token. And it works like this. The client chooses a new random serial number, creates a blind challenge from that, and then the client shows the token it already has and this blind challenge to the server. The server verifies the token. For example, does the signature actually verify? Was it my signature? And also if the token serial number is already in the database, the server signs the blind challenge and inserts a serial number in the database. So now it's spent, this old token, and then the client unblinds the signature and has this fresh token now. And you see that this unlinkable property holds. So this old, the server at this point has only seen the old token and it has signed some new token, but because it's a blind signature, it doesn't know how the token actually looks like that the client now has. And this reissuance protocol is also used for payments. So if Alice wants to pay Bob, then Alice just gives Bob the full token, and then Bob will try to engage in a reissuance protocol with a server, and either this succeeds because the token has not been spent yet, or Alice tried to attack Bob by previously spending it somehow, so the server won't reissue and Bob won't ship whatever, the t-shirts or hats, so on. Okay, so in this section we would like to get to a protocol where you can buy a blind signature using Bitcoin without having to trust anyone. So the buyer will definitely get the blind signature and the seller will definitely get the Bitcoins. There's no way to cheat. And the first step towards that is we need to define a protocol for how to exchange a discrete logarithm for Bitcoin. So let's say the buyer wants to buy the discrete logarithm of some point t, which is small t multiplied by the generator from some seller. And this is like the basic scriptless script technique. So what happens is that the buyer first creates a multisig output with a seller. This would be something like it would be a 2 of 2 multisig. Then the seller sends a transaction which sends the coins from the multisig output to the seller, and an adapter signature with T to the buyer. And I don't want to get into what exactly the adapter signature looks like. You can Google Scriptless scripts or look in the references I've included at the end of this talk. But we see what this is used for in a moment. So the buyer gives the seller now her signature over this transaction. So now the seller can spend the output using the transaction that was already signed by the buyer. And by doing that, the buyer learns the actual signature over the transaction from the seller, and using the adapter signature can now compute the discrete logarithm of t. So the only thing that happens on the blockchain is a single transaction, and this is like just a normal payment. Nobody looking at the blockchain can see that this is actually happening off-chain. Okay, so doing these things, payments on-chain is nice, but even nicer would be if we could also do the same thing, namely buying discrete logarithms, but with Lightning Network payments. And this is currently not supported in the Lightning spec, but maybe in a future version using a technique called multi-hop locks in place of HTLCs. This has also been discussed before on the Lightning Network mailing list under a different name, mainly scriptless scripts with Lightning. But some researchers recently put out a paper where they actually proved that this construction is secure, and they used the name multi-hop locks. So let's first look at HTLCs at the moment. So the buyer sets up a payment route to the seller through one or more hops, and each lock is basically a hash of some pre-image. And as soon as the seller sees this route, she can try to claim this payment using a pre-image. Then the hop will learn the pre-image P and can itself claim the payment. Okay. Now these multi-hop locks, they use curve points instead of hashes as locks. So similarly, the buyer sets up a route, but this time the locks are L1 and L2, which are points, and wants to buy, as before, the discrete logarithm of some point t. And now also, again, the buyer exactly controls how these points look like. So the first point, L1, is the point t, the point that the buyer wants to buy the discrete logarithm for, plus some L1 times g, and L1 and L2 are just randomly generated numbers by the buyer, and L2 is just L1 plus L2 times g. Then, while setting up this route, the buyer gives L2 to the hop and L1 plus L2 to the seller. And now the seller knows how to claim the payment, because now it knows the discrete logarithm. The discrete logarithm is just t plus L1 plus L2. T it already knew before, L1 plus L2 it got from the buyer. Now the hop sees C2 and can compute C1, which is the discrete logarithm of L1. And the buyer, seeing C1, can now compute T by just subtracting L1 from C1. So yeah, that's basically it. And now how can you buy blind signatures this way? And one building block you need is so-called committed R-point signatures. They have also been used, for example, in discrete log contracts. And so how they work is the seller creates a public nonce R, and then the buyer can compute the seller's signature S times G. The seller cannot compute the buyer cannot compute the seller's signature, because otherwise the signature scheme would be broken. But it can compute S times G, and this is just computed as R plus the challenge times the public key. Okay. And these committed R-point signatures, they don't only work for regular transactions, for regular signatures, they also work for blind Schnorr signatures. So the client can compute the server's blind signature S times G, and then can just buy the discrete logarithm of this thing with bitcoins either on-chain or off-chain using above techniques. Okay, and now that we are able to buy blind signatures for Bitcoin, we can look at the technique called a blind coin swap. So a coin swap is a very old privacy technique where Alice has some coins, Bob has some coins, and they can atomically and without being able to cheat each other exchange those coins in order to break the history of the coins and make blockchain analysis much harder. And the point here with a blind coin swap is that there's some kind of server who does coin swaps all the time, and this server cannot link with which coins or with whom these coins were swapped. In that sense, it's very similar to Tumblebit, but it's only based on scriptless scripts, so the blockchain footprint, again, is minimal. You don't see on the blockchain that there was anything else but a payment. If you use on-chain transactions to buy the discrete logarithm. And also I think it's a little bit simpler. It doesn't use RSA or something like that. It's only discrete log based. Okay, so the key idea here is that the client buys a blind signature from the server where the message is not anything, but it's actually a transaction which gives server coins to the client. So let's look a little bit more into how this works. So let's assume the server has a bunch of coins. They are here represented by this box with a server label, and the client then creates a unsigned transaction spending these coins from the server. Cannot sign it, of course, it needs the signature from the server. So what it does then, it creates a blind challenge from this unsigned transaction. It creates a blind signature times G using these committed R-point signatures, and then it pays for the discrete logarithm, which is the actual blind signature it's interested in, and then it unblinds this signature, and this is then actually a valid signature for this transaction from the server and can broadcast this transaction. So the point here is that the payment of the client to the server and this transaction that sends coins to the client is completely unlinkable, because it was only ever seen by the server blinded as part of this blind signature. Okay, so far we've only bought blind signatures from some kind of server, but in most cases that's not very interesting. What you actually want is clients that have some kind of eCash tokens can exchange that without having to trust each other. But the central issue here is that the server somehow needs to make sure that the buyer actually gets the token and the seller gets the bitcoins, and the seller only gets the bitcoins once, so it cannot sell it twice or something like that. So the easiest way to do this is to make the payment being a multisig, a 2 of 3 multisig or something like that, with the buyer, the seller, and the server. But the obvious problem here is that then the server would be able to see who was actually involved in this payment, and also would be able to link a payment to a token. So we don't want that. Another idea would be to have the server part of a Lightning payment route, where the server would be something like the last hop, and then the server can atomically decide whether the payment goes through or not. But we are going to look into something else here, which I think is more general, maybe a little bit easier, which is you have some kind of token which has a lock time, so you can only spend it after the lock time expires. And for that we need to introduce a new eCash system, which is based on so-called branch credentials, and these are like the eCash tokens we've seen before, but they can encode more attributes. So essentially they are like Peterson multi-commitments of the attributes. So now you have multiple generators, not just G, you also have G1, G2, etc. And you have the attributes A1, A2, and you have some blinding R, and you just add these up. Actually, branch credentials look a little bit different, but you can imagine they look like this. And because of this structure, which is relatively simple, it's also easy to prove properties of attributes in zero knowledge. So, for example, does A1 plus A2 equal to A3? Or is A1 equal to A2? Or is A1 within a certain range? So let's look at another example eCash token based on branch credentials. This is the same as before. Similar to before, it has a serial number and it has the server's signature, but now it also has an amount and a type. And the reissuance protocol in that case is very similar. The first two steps are actually the same. So the client chooses a new random serial number and a blind challenge. From this serial number, the client shows a token and the blind challenge to the server. But now the client also needs to prove that the type and amount in the old token that it's spending and in the new challenge is actually the same, because otherwise it could create a token which has completely different amounts. So the server needs to make sure of that. Still work? Yeah. Okay. Now, back to our original question, how can we have a buyer and a seller trustlessly doing this fair exchange of Bitcoin and eCash tokens? We say that there's now two versions of the reissuance protocol. One is the normal one, where you just get a fresh token. The other one is one where the token seller actually receives two tokens with the same serial number. So you can only spend one of them. And one of these tokens is the buyer token, which is similar to before, except that it also encodes a buyer secret only known to the buyer, and a seller secret at the beginning only known to the seller. And this token is only reissued by the server when you prove the knowledge of the buyer secret and also of the seller secret. And then there's the seller token, which is similar to before, except that it also has a lock time. So this is only reissued by the server when the lock time is over. So the exchange works like that. The seller gives the buyer token to the buyer, but without the seller secret, because the buyer is going to buy the seller secret. Okay, and it proves that the lock time of his corresponding seller token is sufficiently far in the future such that the buyer has time to buy this token. And then, since the seller secret, since attributes are just discrete logarithms of some points, it's possible to use the techniques we've seen earlier to use on-chain or off-chain payments to buy this discrete logarithm, the seller secret. Now, either the buyer can run the reissuance protocol with the server, because now it already knew the buyer secret, now it also knows the seller secret, or the buyer becomes unresponsive and the seller runs the reissuance protocol after some lock time. Okay, so in conclusion, we've seen that blind signatures can be useful in general Bitcoin smart contract protocol designs. For example, we've seen the blind coin swap, and it's possible, probably there are also other ways to do this, to build trustless off-chain or on-chain eCash token exchange protocols using just scriptless scripts. So in the case of off-chain, there's really no blockchain footprint at all. Eat that, CryptoKitties. So the next steps, I think, are first, we want a Schnorr soft fork. Most of the things, I think everything except these committed R-point signatures which are needed for the blind coin swaps are also possible with ECDSA. But would be better to get Schnorr, because Schnorr has also some other nice properties that we want to have. So probably there will be a Schnorr proposal in the next months. If you see it, review it, provide feedback, advocate for it if you like it, implement it in your own software. And also we've seen that Lightning V1 is great, but we also want scriptless scripts in Lightning to be able to buy these discrete logarithms and then also blind signatures and so on. Okay, so these are some references. You can find the slides here, then you can click on the reference if you're interested. Thanks for your attention, thanks for inviting me, and I'm happy to take questions.
I just wanted to ask, why did you use blinded Schnorr signatures?
Compared to?
Compared to the traditional way of blinding?
That is because the verification of a blind Schnorr signature and a Schnorr signature is the same. So that means that, for example, we can do the blind coin swap, because what the server does is it creates a blind signature, and if you unblind it would actually become a valid Bitcoin signature, which you cannot do with RSA, right? Because there's no RSA signature scheme in Bitcoin.
Thank you.
What is the implementation status of any of this?
We first probably want to spend effort into having a good Schnorr proposal, and then I think it would be very interesting to implement branch credentials in libsecp, and then of course there need to be some stuff on top of that. That depends on how many people are actually interested in doing that.
Thank you. So there's this new fuss around BLS signatures. Mm-hmm. What is your opinion? What are the trade-offs? Have you looked into it?
I haven't looked that much into it. I think some of the fuzz makes sense because you can really do really cool things with it. For example, you can aggregate transactions non-interactively, whereas so for example, we've seen the coin join stuff in the previous talk, and you could do that non-interactively with BLS signatures, but BLS signatures have the downside that they require new cryptographic assumptions, and they're also quite a bit slower actually.
Just a small thing that might be obvious, but I didn't get. So in the buying the discrete logarithm use case, is the answer revealed publicly on the blockchain, or is that private on only the buyer becomes aware of it?
Only the buyer becomes aware of that. It's not at all on the blockchain. Just the signature on the blockchain is enough for the buyer to compute the discrete logarithm. And this signature is indistinguishable from any other signature. Okay then, thanks again.